Hello, 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 DJ.
So, hi all, welcome to Aries seminar. So, I think everybody can sit just on the places. Yes. So today we have Dr. Priyanka Chaturvedi from TIFR Mumbai. So she will talk about from Jupiter's to Earth's, exoplanets and beyond. So before that, let me introduce the speaker. So Priyanka Chaturvedi is a reader at TIFR since June 2024. She is an expert in exoplanet detection and stellar spectroscopy with a focus on radial velocity studies. Okay. So she did her PhD in PRL Ahmedabad in 2016 on eclipsing binaries and radial velocity studies. Okay. So she had a long tenure at Thüringer State Observatory in Germany for a duration 2018 to 2024, where she secured German Research Foundation grant as a principal investigator. She leads the planet working group of the International CARMENES consortium that aims to search for habitable planets around M-dwarf stars in the solar neighborhood. So I think there are many young faces for you. This talk can be something you can learn about our own planet. You already know about our own planet. You will be learning about exoplanets and the current research. With this, I invite Dr. Priyanka for the talk. Please go ahead.
Hello, good afternoon, everyone. I think I'm audible. Okay. So welcome everyone to the colloquium. And it's a great pleasure for me to be present here at Aries. And coincidentally, it coincides with the ATSWA school. So it's very nice to have so many young faces attending this colloquium. So first of all, thank you, Jagdish, for giving the nice introduction. And also thank you, Jeevan, for inviting me here. It has been a pleasure throughout. And I'm really looking forward to the Devasthal Observatory trip tomorrow. So this is my first time in Aries and also in Nainital. So thank you for having me. Okay, so what we are going to discuss today is about exoplanets. So humanity has been interested in this topic of exoplanets since a very long time. So as early as 1950s, people were trying to look for exoplanets, but the first successful detection only came in the year 1992, which was also a serendipitous discovery. So there were a group of astronomers who were studying pulsars. And so pulsars are stars which are at the end stage of its evolution, and they are emitting very radiated beams. So the period of these pulses are extremely accurate and they do not change usually. But what the astronomers found that the periodic pulses which were supposed not to be changed, they were actually changing. So this was because of the presence of an additional body in the system. So they finally discovered that there were additional planets in the system. So this was a very interesting discovery. Not many detections have been made by the pulsar timing method, but this happens to be the first kind of detected exoplanets. What happened nearly 3 years was something which led to what we are currently witnessing, an increase of the number of exoplanets that have been detected. So these two gentlemen that I've put on the slide, here is Michel Mayor, and his then student Didier Queloz. So they worked at the Geneva Observatory, and they discovered the first exoplanet around a solar type star. This led them to win the Nobel Prize in Physics in the year 2019. Now, what was so special about this discovery? So interestingly, this planet 51 Pegasi b, now why do we call it B? So the nomenclature of every exoplanet which is discovered around a star is such that you have the star name 51 Pegasi, which means it's around the constellation. It's in the constellation of Pegasus. And B is the planet which is discovered. So the first planet which was discovered in the year 1995, interestingly, it has an orbital period of 4.2 days, which means that it orbits at this period. And the mass of this planet is just half that of a Jupiter mass. Now today, more than 5,800 exoplanets have been discovered. Now, but just let's take a small fraction of a second or a few seconds to understand this and compare it to our own solar system. Just have the perspective. The closest planet that we have in our solar system is Mercury. It's very small. The mass is really tiny, and it's orbiting at a distance of 88 days. So this is really far from its host star, which is Sun. And here comes a planet which is pretty massive, almost half that of the Jupiter mass, and it's orbiting very close to its host star. This was something which completely boggled the astronomers who were looking at it. It took them a lot of time, though they had these confirmations in 93 or so. Many astronomers took a lot of time to make this confirmation, because it was hard to convince them, to the community, that there can be a planet which can be so close to its host star. So what you see here on the right side, the pointing is somewhere in the other direction. Okay, so what you see on the right side is the radial velocity curve. Now, what all this is, we will be discussing in the next slides, but this is what the discovery plot of the paper, the discovery paper, shows. So let's proceed. Let's look at this slide. It talks about the exoplanet discovery by methods. So now there are several methods to discover exoplanets. So as we pointed out, since 1995, we started to detect exoplanets. Look at this graph. There is a continuous increase, almost nearly exponential. So since 1995, the number of planets have really increased. Now, what do you see in different colors? The colors indicate the different detection methods. So the planets which have been detected by transit method, they are colored in purple. The next dominant detection method, colored in green, is the radial velocity method. And we will be mostly talking about these two methods in this talk. And the next other methods, the pulsar timing method or astrometry or such, they are there, but they have not contributed the most to the exoplanet discoveries. So just to be complete, we will not be touching on this, but we'll try to concentrate more on the transit and the radial velocity detection technique. So what you can immediately notice from this plot, that there's a lot of discoveries which happen in the purple color. The reason being, there are several space-based telescopes which are put out in the space, which lists out or digs out several exoplanets, and they do it in one set. Many of such discoveries are made, and the next one is radial velocity. So these are still the most popular ones. Yeah. Yes, so you can also, if you see here, in the initial years of the discovery, most of the planets detections are in green color. So it was dominated by the radial velocity method, the method which fetched the Nobel Prize in Physics 2019 to Michel Mayor and Didier Queloz. But later on, with the launch of Kepler and TESS, the scenario has really changed, because earlier, if you do only by ground-based photometry, number of detections cannot be so huge. But with space-based missions, this has really exceeded far lot. Okay, so we talked about the radial velocity method, what this method is really about. So this method is nothing, but it depends on the Doppler shift. So if you have a star and a planet system, what really happens is that both of these objects go around the common center of mass. We're used to studying in school that the planet goes around the star, but in reality, it's the star and the planet which both go around the common center of mass. So there is no light that you're getting from the planet. The light that you're getting is only from the star. So whenever when the star goes around the common center of mass, in orbit, there will be a phase when it will be away from the observer, line of sight, and at some phase, it will be coming towards the observer in Earth's line of sight. So if you happen to take the spectra at that time, there will be Doppler shift, which will be observed. This is something very much related to the Doppler effect of sound that you might have observed. An approaching train, and the frequency of the sound is higher when the horn is there and the train is approaching you. And as it is receding away from the platform, you see that the frequency changes. So this is the same effect which happens in light. And since the motion of this star goes around and it depends upon the orbital period of the planet as well, since this is very, very periodic, one is able to detect a planet and also know its period and several more properties. How? Let's just have a look. So we have this nice cartoon which is provided by NASA. Let's look at this. So this is the same thing in a video format. So you have the star and planet system. Now, yeah, it's important to note that this system is edge on, which means this is the orbit of the system. If the system happens to be face on, there will be no change in the appeared speed or the radial velocity of the star, and this will be still zero. So that's why it's very important to understand that this particular system has an edge on orbit, and at each instance, as you see from the observer's perspective, when this particular object is going or moving away from the moving towards us or going away from us, you see that the spectra has changed its color. So let's start to also relook at it again. So there is this spectra which is happening. So as it's going away, you see that it's red shifted. And as soon as you see that the star is approaching us, there will be the spectra. Whenever it's taken, it will be appearing blue shifted in color. So this is very interesting. Again, I would like to remind you that there is no light which is coming from the planet. One is only being able to take the light from the star. And since this appears like a disk completely resolved, but actually normally the stars you cannot resolve. They are point sources. So you will get light only from the total star when you're making these measurements. So what do we do really to proceed with this information? So you are taking spectra at different instances of time of the star. So what you really get is a spectra, which means its intensity versus wavelength. Now, what does Doppler effect tells us? That you can convert this wavelength shift into velocity. So your delta lambda is nothing but your delta V by C. So you can easily convert this wavelength shift into velocity shift. So how do we do it? On the dotted line, I hope you can still see it in the contrast on the slides. So this is the spectra of the star that we don't know whether it has shifted or not shifted. What you see on red color is a mask. So it's like a theoretical mask, and it has a value of 1 wherever you are supposed to expect that there is a line which is present. Now, all these lines that you see in the spectra, this is nothing but absorption lines from the elements. So I think you had a couple of introductory lectures already in the school. So you might be aware that on the photosphere of the star, there are often elements which causes absorption. And because of this, there is an absorption spectra that you are getting. Now, these absorption spectra, if you are taking a high resolution spectra, you can really resolve these lines very well. And these lines, when you are trying to match it against a theoretical mask, which means you're trying to see where exactly a wavelength, zero velocity wavelength should be present, you do a cross correlation, which means you slide this mask across this velocity, and at the position where the match is the most perfect, like in this third figure, you see the dip in the line. So this is the minimum of the cross correlation function, which means that has the maximum match, and this is your true velocity of that particular thing. Now, you do not work with a single line. As you can see here, there are 3 lines which are shown, but in reality, there are several lines. So the mask extends for a very large wavelength range, and it has several lines. So the beauty of this exercise is the more number of lines that you have, you would be able to get a very high radial velocity precision. So more number of lines, your statistical error bars on each velocity measurements would be lower, which means in turn, you would be able to measure the smallest possible masses. That's why it's important to go high resolution, because if you go high resolution, then these lines are really separated out well. And if you have a very broad wavelength range, then also you have more number of lines. Now, this can immediately translate into that you cannot work with stars which do not have enough of such photospheric lines. So there are stars in our galaxy which are very hot, O or B type stars. They are not known to have many such atmospheric lines because the fact that they are very hot, they only have ionized hydrogen or helium, and these lines are also very broadened, not enough to do precise radial velocity measurements. Hence, traditionally, most of the radial velocity measurements have been done on solar type stars. That is why there has been an observational bias that you detect more exoplanets around solar type stars with this method, with the radial velocity method. So this is how then a typical radial velocity curve looks like, the one which we also saw in the discovery plot of 51 Pegasi b. So what we see here on the y-axis is this radial velocity that one has measured. So remember, this is a model. So on each point, you will make some observation. Let's see you take the spectra today, then you again go on the next night and make an observation. You will have a point here, some point here and here, and then you fit it with this curve. Amplitude of this curve is called as K, which is actually has the value of mass imprinted in it. Now, since this is radial velocity, we always measure the V sin I. So I pointed out that you only can work with this method when the orbit is edge on. So actually, you are just measuring the sine component of it. If the orbit is face on, the sine, the angle of inclination is 0, and any value that you measure comes out to be 0. So that's why the mass is also not the true mass of the system that you get from the radial velocity measurements. It's always the projected mass. So whenever we say that we have found mass of a planet with the radial velocity method, we would say that it's MP sin I, or it's the projected mass. That's what you see in this equation. So this is all, you can derive this equation through Kepler's law. The second law and the third law will be able to bring us to this equation. And if we just put it into simplistic terms of Earth and Sun values, then what you see here in this equation, if you have an orbital period of 1 year and the star is exactly of the mass of Sun, and the planet is exactly the mass of Earth, then you see this K value is 9 centimeters per second. This means in order to detect an Earth-like planet around a Sun-like star, we need this radial velocity semi-amplitude to be 9 centimeters per second. This is a very, very, very small number. And in order to make such a detection, you need at least 2 to 3 sigma level precision, which means your spectrograph has to be stable up to 2 to 3 centimeters per second. This is a feat which is very, very difficult to achieve. It's not an easy exercise. So in current scenario, over the globe, there have been several precision spectrographs which are operational, and they're trying to search for exoplanets. And the best they're able to do is 20 centimeters or 30 centimeters per second. So the reason one is because you need a larger telescope, a better detector, good pipelines to make these measurements, and also you should be able to understand what your star is doing. Now, there are several people in Aries who would agree with me because they are working a lot in stellar physics. They would know that there are several interesting things that the stars do. But for people like us who are just interested to detect exoplanets, we call this as noise. So we want to get rid of this stellar noise because this is something which is hindering us to detect the smallest of the exoplanets. But this noise is a very big difficulty or a big challenge for exoplanet hunters to remove this or to model this in our signal. So this is a very forefront research area which is currently going on in the current era. So we will also touch upon some of these things in the next few slides. So let's also move to another popular detection method which had the most discoveries, which is the transit method. Again, always remember, just for the illustration purposes, we see the disk of the star as resolved. But in reality, you would never be able. It's only Sun that we can resolve. All the other stars, they are unresolved. So here what you see is that a planet is crossing in front of the disk of the star. And before the crossing happens, you see the total intensity of the star. And as soon as the planet starts to occupy the disk of the star, you see a decrease in the intensity. So this is nothing but a transit light curve. And one would be able to measure the duration and the period and the inclination from this effect. So the same thing, we have again a very nice cartoon video illustration by NASA. So let's have a look at this. It's very similar. You have again an edge-on system. This will also not be able to be observed if you have a complete face-on orbit. It just does not work. You have here on the left side, you see a light curve. And as soon as the star as the planet goes in front of the star, you see this is a decrease in the intensity. So this is how your transit method works. Now, in some cases, for some systems, you can do both, which means you can also do the transit method and the radial velocity method, which is a bonus because you would be able to get the radius of the planet and also the mass of the exoplanet. And this is very interesting because you can talk then about the density. Mass per unit volume is density, so you can talk about these things. Now, interestingly, the first transiting exoplanet, this was discovered in the year 2000. So we talked about the radial velocity detection method. This was in the year 1995, but it still took 5 years for people to discover a first transiting exoplanet just through transit. Why was this the case? I mean, normally you would believe that discovering a planet through radial velocity appears to be more complex because you need to have precision spectrographs. It has to have a spectroscopy component. This seems a rather easy method. But one also has to remember, if you have no prior information when the transit happens, you nearly have to observe the star for a very long time to actually capture the transit, which happens only for a few hours. And the remaining entire orbital period, which could be like 88 days or 10 days or 12 days, whatever it is, there is nothing which is happening. So the starlight will be constant for all the time. And only when the transit happens, there is a decrease in this light. But for radial velocity, since it's a continuous phenomena, you're always measuring the V sin I, there is some velocity information at each point in the orbit. So even if you do happen to record it from ground, there is still every time you get some measurement. But recording this from ground and doing it right on your own without any prior information, it takes time and patience. That's why it took some time for the first transiting exoplanet to be discovered. So this was this particular system, and they discovered this from ground through one of these STARE projects. Now, whenever this measurement was done through space, naturally this light curve looks much better. I forgot to put in a image which was also taken for this same transiting exoplanet through space. So naturally, if you go to space, then the advantage is that the error bars on each point reduces, and you're also not worried about the day and night cycle, which you are affected on ground, and you are above the Earth's atmosphere, so you do not have to worry about many such things which atmosphere accounts for. Now, we spoke about these planets through transits and radial velocities. You might have immediately noticed that most of the planets detected have a very short orbital period. So the planets which are much like almost as massive as Jupiter, or typically 1/10 or 1/4 that of the mass of Jupiter, and they orbit their host stars at an orbital period lesser than 10 days, they are known as hot Jupiters. So they are like Jupiters, but they are not Jupiters, because our Jupiter in our solar system, this sits at 5 AU. But these particular Jupiters, they are situated at probably 1/10 that of an AU. So they are very close, and because of that, they get a lot of stellar irradiation from its host star, and hence they are known as hot Jupiters. Now, since these are located very close to its host star, the immediate consequence is that they are very easily detected by both the radial velocity and the transit method. So because on the transit method, they have a very larger shadow that is casted. Everything depends upon RP by R star. RP is the planet radius and R star is the radius of the star. So if this ratio for a planet which is larger, this ratio would also be larger. If the planet radius is very small, then the ratio of RP by R star is smaller. So naturally, if the radius is larger, it is easier. The transit depth is very huge, and it is easier to detect this depth. But if the planet is orbiting at a very large distance, then it takes longer time to make this confirmation. You at least need 2 transits to have the confirmed period. And also the depth could be smaller for smaller planets. Similarly, for radial velocity methods also, since the planet is closer to the host star, the pull of the planet on the star, it's the gravitational pull that the planet is casting on the host star. And because of that, this pull would be larger, and hence it will be easier to detect. The K value will be higher. So if the K value is of the order of meters per second, it is in the reach of many spectrographs worldwide, and it's easier to detect larger planets. But it is slightly trickier to detect smaller planets. So Earth-like planets are always difficult to detect compared to Jupiter-like planets. Hence, there were initially, in the initial phase of discovery, since 1995, there were many Jupiters which were discovered in the first few years. Now, why hot Jupiters are not seen in our solar system? We don't know really the answer, but something that we saw outside our solar system only. That was very interesting. And that is actually the reason why Nobel Prize in Physics in the year 2019 was given to this. I mean, it was rather easier to discover the planets, but still very difficult to explain how can such planets form so close to their host star. In our solar system, the way we explain the formation of Jupiter is through core accretion, which means that you have sufficient gas and then you are accreting, like smaller and smaller material of gas and pebbles is getting accreted, and then you are building a planet out of it. And at the outer part of the disk, beyond the snow line, there is sufficient such material to build such planets. But if you are very close to its host star, because of the temperature, there is not enough gas. So in reality, it's very hard to build such a massive planet so close to its host star. Then how do you explain such planets? So there are several theories. Most of the theories agree that there could be that these planets are formed at a great distance from its host star, and then they have migrated over the years closer to the host star. So either they migrated because there was an interaction of the disk. You know that when planets form, there is a disk which is surrounding its host star. So either this disk interacted, and because of this interaction, slowly these planets move inside, or maybe there was a third body in the system which caused the eccentricity excitation and initially caused tidal migration and led this planet move closer to the host star. So these are still, I would say, unsolved problems in the field of hot Jupiters, though they are easy to detect, but very hard to explain. And this is something which theoreticians are trying to still work on. Now, we looked at several such hot Jupiter candidates from various sources, and we could also, so what you see here on this graph is a plot of temperature, the equilibrium temperature, and the radius of such planets. So in blue are all the Jupiters which have been discovered, the hot Jupiters have been discovered till date, and these are some of the planets that we could detect by some of the surveys that we ran on some spectrographs. You can notice that most of these targets have temperatures very high. So most of these planets, they have a high temperature, means they have planet temperatures more than 1000 or 1500 degree Kelvin. So they are very hot. Now, what does this imply? So maybe some of you would have heard about JWST. So JWST is doing many kinds of amazing science. One of the things that JWST is also trying to understand is the atmosphere of exoplanets. Now, in order to understand the atmosphere of exoplanets, there has to be sufficient temperatures, because this makes it a good metric in order to look at such atmospheres. So hot Jupiters which have higher equilibrium temperatures, they are excellent candidates to supply to space-based telescopes like JWST. So they are very interesting in that context. But of course, there are also some of the targets which are not so excellent, but while discovering, we did detect some of these. And most of these planets also have a radius which is slightly larger than what was expected. Now, why does this happen? So if you keep a planet which is so close to its host star, naturally, because of a lot of stellar irradiation that is getting casted on because of its host star, the radius of this planet gets bloated. And this is why typically through models, if you would believe there would be a certain planetary radius, they appear to have a slightly larger radius that you see in these targets. Then there were some interesting discoveries that we made. One of this that I would like to highlight is of a very young hot Jupiter. So this hot Jupiter has a very large error bar on the age estimation, but it's definitely less than 1 giga-year. So it is typically a relatively young hot Jupiter. And we looked at several clusters and tried to place our star for age determination by looking at the lithium lines. So some of the stars have lithium lines and they are supposed to be young. So we used this lithium line measurements to place a constraint on the star. And we also, this particular star had observations from TESS, which is a space-based transit mission. We could detect the radius, we could measure the radius through photometry. And we also did spectroscopy by the spectrograph, which was present in my previous working institute where I was there in Germany. So we did this observations and found out that the planet has a mass of 2.3 Jupiter mass and a radius of 1.44 Jupiter radius, and it orbits at a very close orbital period of 1.5 days. So this is a very common system detected, but interestingly, it happens to be around a young star. That makes it very interesting. And why people want to detect stars around young systems, the reason is because we want to understand where exactly the planets would have formed. So if you are able to detect planets around very young stars, then it makes it interesting, because then you can comment on where the planet at what stage it would have formed. Whether it is really having the time to migrate or there is just no time for it to migrate, then it would have just formed right in situ, which means right in place where you observe it. So these can only be constrained by looking at very young stars. So this happens to be one such study that we participated in. Now, there was an other interesting thing. Now, you might be wondering, is there only always one planet in the system? That's not usually the case. There can be multiple planets transiting or multiple planets present in a system. So this system was initially detected by TESS. We had only a very deep light curve, which was easy to detect. And we thought that there is just one Jupiter present in the system. But we went on measuring its transit. We realized that the transit time, the central transit time, each time when the planet comes again in front of the star, this is very periodic phenomena. If it happens at 4.4 days, every time it should repeat at 4.4 days. But this was not happening. We saw that this central transit time is actually varying. And when we did the analysis, we took a lot of data. There was a lot of test sector data available. And when we looked at it for a long time, we realized that actually the transit time is varying. Then we looked deeper into the data and realized that there is an inner planet which is present in resonance 1:2, which means that it has its orbital period at a ratio of 1:2. So there was an additional planet at 2.2 and it was present interior to this hot Jupiter. So there was an additional Neptune which was present in this, or a super Earth which was present there in the system. And we did not know it beforehand unless we did patiently wait and took data. So sometimes you might just want to publish your source thinking, oh, there is one planet at 4.4 days, let's publish and get done with it and never reobserve it. But that is not the case. If you keep on observing the systems or looking into the data carefully, there might be additional things which are hidden in the data. So there might be many things which are published, but you never know. If you look into the data, there might be still more discoveries which are there, letting you uncover more things. So this, we could do it. And of course, anybody who has a little bit knowledge or gets trained can also do that. So how do we get on detecting these exoplanets? Are there any such things present in our neighborhood? So while I did my PhD at PRL, I was associated with the spectrograph PARAS, which is a facility at Mount Abu. It sits on a 1-meter telescope. Currently, it is not working, but it has its elder cousin or brother or sister, whatever you call. It has a PARAS 2, which is on a higher or bigger telescope, on a 2.5-meter telescope. And it's also replicating the similar science goals, is trying to look for exoplanets. So this is an inside view of the instrument where it is kept in pressure and thermal environment. So what you see here, these black things, they are kept in a pressure and thermally system. And why do we need this? Because any variation, any mechanical variation that occurs actually affects the radial velocity variations. So since we are talking about these few centimeters per second, we need the system or the CCD to have a very, very stable temperature and very, very stable pressure. And that's why you put it into such a thing where it has no ambient effect from the atmosphere. Then there was another telescope, which since I was working there for 6 years in Germany, I still collaborate with them. And this is a 2-meter Alfred Jens telescope in a very quiet town in the eastern part of the Germany. And there we had the largest Schmidt corrector plate telescope, and we also had a high resolution spectrograph that we took data. So the previous discoveries that I showed, they were through these particular telescopes. Now, we will be shifting gears slightly. So if you have any questions in the first part of the talk, it will be a good idea to ask, and then we'll start to talk about some other interesting things. Yes. Yeah, so I mean, in transits, what you really do is you phase fold the data. So unless you phase fold this data, you would have no information. Now for us, actually, we wouldn't be looking for it. There was no way to know this. But since we had a lot of transit data available, we saw that the transit time is shifting. This can only happen if there is a gravitational third body in the system, which is perturbing because the center of mass is changing again because of this third body. This made us look into the data. But even when you're in the first place, you're trying to look for transits, what you really do is you do the box least square fit, which is you are phase folding the data and trying to see this transit-like signature. So you do this typically on all the data sets to see how many planets you can discover. Sometimes they get not detected by the pipeline, but if you have additional information, then you can particularly try to look for it. So we tried to narrow down our search at this period. Yeah. If the data is not available, you never know. There might be planets, but you cannot, I mean, this is only proven unless you find it. There might be more systems. We can never say that there is no planet in the system because we don't detect it. There might be something, but we are not capable of detecting it. That is the only thing we can say. Okay, so now just let's have a look at this. This is the number of, again, a similar plot that we looked at, the total count of exoplanets plotted as a function of the planet radius. So what you can notice here, there's a lot of detection which is happening in the small radius of the planets, which means that small planets, planets which have a radius of less than half that of Jupiter radius, they are the most common detected planets. So we understood by the radial velocity and the transit method that it should be rather easier to detect larger planets. But even after so many years, nearly 30 years of planet detection, what we have found is that they are not the most common detected planets. They are not the most common detected planets. The planets around 1 Jupiter to 2 Jupiter radius. Still, the small number of planets exceed, which means this has something to do with not just observational bias, but the way planets actually form. I mean, I'm not a theoretician to make a comment more on the theory side, but this is something which has been observationally found. So how do you really go on confirming smaller planets around host stars, which are different kinds? So when we talk about Jupiter-like planets, a typical radial velocity precision of few meters per second, 3 to 5 to 10 meters per second is also good enough, because these Jupiters have really large radial velocity semi-amplitudes up to sometimes 50 or sometimes 10 to 100 meters per second, and anything 3 sigma detection, you can just have few meters per second detection. But if you want to detect planets which are really small, then you need different kind of spectrographs which are called as precision radial velocity instruments or extreme precision radial velocity instruments. So these are two discoveries which we did in the past 1 year, and I'm just putting this out. So what I have plotted here is the transmission spectroscopy metric. So just to bring in perspective, basically it means how good this a candidate is to do atmospheric studies on it. So if a planet has a relatively higher temperature, a higher radius, then the larger value of TSM is normally evident. So we found out two systems which have, so this is the one which we are putting out here. This is TOI 3493b, is recently got published. I mean, it's accepted and it will be published soon. And this is another system that we published 6 months ago. Both of these systems are on slide around stars which are different kind. This is around a solar-like star, and this is around an M dwarf, which is slightly lesser mass star. And they have a high TSM, which means they would be very good candidates to be supplied to JWST, or if possible by ground-based measurements in the future when we have really large telescopes which are there. So how do we really go on? Why do we really want to do such studies? So if you look at the distribution of stars which have been looked host stellar temperature, then you note that there is a lot of search which is happening around this domain. Most of the host stars with confirmed exoplanets come in this region, and also around stellar surface gravity, they come around this region. But talking about this particular region, which is the M dwarf domain, is not very well studied, and even again, lower temperatures is not very well inspected. Why so? Just look at this plot. So this is a very famous spectrograph HARPS. Maybe some of you would have heard of. It has contributed to hundreds of planet discoveries. It is operational in the optical wavelength regime from 380 to 680 nanometers. Most of the stars which are solar-like you can see here, F2, G2 or K2, all these are solar spectral type stars. They have their peak thermal emission peaking in this optical regime. But if you want to look at M dwarfs, AD Leo is one example, which is an M dwarf, M3V. This is shown in red. The curve is shown in red. You see that the peak, the black body peak, does not happen in the optical wavelength regime. So if you are looking with HARPS for such a spectrograph, you will only be able to target this portion of the spectra. So the energy or spectral energy distribution, which means it will be very faint in the visible. But if you want to focus or target such stars, then one must also have a wavelength region covered, which is more sensitive to that region. That's why near-infrared spectroscopy has been started in the last decade to look at stars which would have slightly lower temperatures. So in the last decade, there has been several instruments. CARMENES is one of them. which I participated while I was in Germany, and I still am contributing to the efforts of this survey. And there have been also many other interesting instruments like the Habitable Zone Pathfinder, which sits on a Hobby telescope, or the Maroon X instrument, which sits on Gemini. These are very exceptional, good quality instruments which are now operational in the near infrared, and they're trying to look at M dwarfs in particular. Now, why M dwarfs? Why they are so interesting? Now, while we were looking at these transits and radial velocities, we only talked about the size of the planet, how massive the planet. So we concluded that if the planet is more massive in size, or if it is larger in size, it is easier to detect. On the other hand, if the star is smaller, or the mass is also lesser, it's also easier to detect, because again, this is the ratio which is mattering. MP by M star, the mass of the planet versus M star, or the ratio of the planet radius by the ratio of the star. So if you cannot increase the radius of the planet, if you don't want to do that, reduce the radius of the star. So if you change your host star, you might be able to detect Earth-like or Neptune-like planets and understand how they are formed. So there have been many discoveries in the recent past around such M dwarfs as a consequence of this endeavor which has recently started. So I participate for this CARMENES survey. It is on a 3.5 meter telescope sitting in southern Spain, and this particular spectrograph has two channels, which means it has two arms. One of them is in the visible, which is 0.5 to 0.96 microns with a resolving power of 84,000. Now, resolving power of 84,000 just means that your delta lambda by lambda is such a number. So at any given wavelength, if you're talking about, let's say 1 micron, how much you're able to really separate two wavelengths. So this number is very high. That's why it's a high resolution spectrograph. For typical studies, when we do extragalactic studies, we are also good with resolving power of 1000, where we do not really need to resolve high separations, and also these targets are far distant, so you would not even have good signal to noise ratio. So now both these channels, as we talked previously for instruments like PARAS, that this is kept also in a pressure and thermally stable environment. This is a very need for the day. Now, what CARMENES is actually doing, it is a radial velocity survey which is targeting 300 M dwarfs. So this is a survey which is conducted only for M dwarfs. Its spectrograph can also look at other stars, but since it is designed in a way to focus on low mass stars, it is conducting a survey of 300 plus M dwarfs, and it's trying to systematically make measurements of all the stars which are available from this 300 lot, and trying to understand what all planets were present. It was started since 2016, much before I joined the consortium. Till date, more than 60 planets have been confirmed, and out of which 9 are in the habitable zone. I would like to emphasize, finding a planet in the habitable zone does not mean we have detected life. It just means we have found the planet at a distance which would have the most suitable conditions of life as far as we know. So there have been 60 planets discovered. Now, what would I like to show on this plot? There is a plot of planet mass on the y-axis, and on the x-axis is the stellar mass. Anything which you see with black in color are the planets which are detected in the literature. Everything in the past by the radial velocity method. Now, anything which is colored in red and blue happen to be CARMENES discoveries. The blue ones also have transits from TESS, and the red ones are completely radial velocity candidates. You can notice that before CARMENES, most of the targets that were detected were around stars more massive than 0.6 solar mass. So traditionally, these are the ones which are the FG and K type stars, which are the solar-like stars, which can be easily looked by spectrographs operating in the visible wavelength range. But as you go towards the low mass regime, there were not sufficient detections. The only reason, because we were looking with not the right kind of spectrograph. And CARMENES and instruments like CARMENES are contributing a lot in this domain, and more number of detections have started to happen. Now, a small summary of what we have done. Nearly what we have concluded in short orbital periods of up to 100 days. For small planets, 1 to 10 Earth masses, nearly every star has a planet. Actually, more than 1.32. This is just because of statistics that you get such a number. There is nothing like 1.3, but it has more than one planet around one star. So up to periods up to 100 days. So this is based on the occurrence rate studies that we have performed on the limited sample that has so far been completed with CARMENES. Now, what do you mean by completed? Which means that we at least have 50 observations of the target being done for sufficient number of time, well distributed over the phase. So we are not concentrating on taking one observation of a star and then going to another star and then third. We try to observe several candidates which are available in the sky, and we try to make an unbiased sample. So keep on observing them without having any prior knowledge, and then you try to see if you have detected a planet or not. So if you have detected a planet, this is a success, but how many planets will truly come out of the survey will be dependent upon how good your instrument is and if actually a planet is present there. So this is how you conclude whether the planet is present or not and how many such are detected. Yeah.
Search?
Yeah.
In making this search, like the distances of the planets are the same?
No. So the stars that we are considering, they would be around not farther away than 150 parsecs. They are not really far away. They are all
Because on the right, you have so many planets. On the left side, you see very less.
You mean you're talking about this side?
Yeah.
Yeah. So these are the masses of the host star. So initially, that's what I wanted to say, that most of the detections of the planets around stars have been around solar type stars. This is what traditionally has been done with instruments like HARPS or so. But with the advent of spectrographs, which are currently focusing around M dwarfs, we have several detections which have happened around stars less than 0.6 solar mass, which are M dwarfs. So
yes,
yeah, so this has really escalated. The efforts have completely changed. And regarding the distance, they are still in the galaxy. They are our near neighborhood. So they are not very far objects. We are not talking about intergalactic here. We just cannot. Yeah. Oh, this was because we just focused on stars looking at M dwarfs. This was a sample which was just curated to look just to focus on M dwarfs because they wanted to do a completeness study of M dwarfs to make advantage of the fact that they can look into NIR and giving the other part that somebody else is anyways looking at solar type stars. Yeah. Right. Exactly. That's a very good point, and that's what we have observed. So I did not point this out, but maybe somewhere here I have written that the number of giant planets that we find from this survey, which only looked at M dwarfs, they were only 6%. So like solar type stars traditionally have a lot of giant planets, but this is absent in M dwarfs. So there is some kind of a ratio, maybe because it depends on how a disk is there. So for solar type stars, the disk is also larger. It has enough material to make larger planets. It also makes smaller planets. But for M dwarfs, we usually find many smaller planets instead of larger planets. This is very much evident in our survey, and also this was confirmed by other photometry surveys like Kepler or so. They also confirmed the same behavior. There aren't enough giant planets. There was a question here, or should I just okay. So CARMENES has a resolving power of 84,000. You're talking about the spectral resolution, right? Yeah. Single spectra, yeah. So you're just looking at the star, the whole light of the star is coming through, and this is the resolving power of it. So 84,000, yeah. 300 stars that is being, so this was when the survey started in 2016, we had 300 stars, and with the launch of TESS, this happened 2 years later than the survey started, few samples were also added to the sample, but they were only to confirm the masses of the transiting planets. That's why they are in blue. So just to point out that we had some information that these could have planets around them, but the red ones are the unbiased ones. So we did not have any information. Yeah. So that has been the typical churn out which has happened. So which means that M dwarfs really have good number of planets, but most of the detected planets that we have found out, they are Neptune size. They are or super Earths or Neptune size. There aren't many giant like planets. This has been Yes, there is a larger, this is an observational bias, and we do have this there. While we do occurrence rate studies, we try to get rid of this bias, but this is true that we have detected many because you detect them faster, so you do publish them as well. Yeah, so that's there. True. Okay. So now some of the interesting discoveries that came out with CARMENES. So this has been a case of a star which is called as Tea Garden star. So there was somebody called Tea Garden this was a favorite star many years ago. It was named like that. And two planets very close to the mass of the Earth, 1.1 Earth mass, they were found at orbital periods of 4.9 and 11.4 days. Now, they were the very first Earth-like planets, which means they have masses very close to Earth-like, but we have no radius measurements because they have no transit measurements. So whatever you could talk about these masses, they are only the projected masses. So we have no information on the true masses. We can just make these measurements on MP sin I. And interestingly, this star is very cool star. It has a spectral type of M7. So detecting planets around stars having temperature less than 3000 Kelvin is actually a challenge. If you want to do it with visible wavelength spectrographs, it's just impossible because there is very little light in that wavelength regime to contribute to any detection. So Proxima Centauri and the TRAPPIST-1 system, it has also detected transiting planets through different methods. So Proxima Centauri has radial velocity measurements, but TRAPPIST-1 system, which is very faint, and it's also an M7 kind star, it only has the planet confirmation by transits. There has been no radial velocity confirmation of the system, but the planets do exist because there is also TTV, which is seen in the systems, where it's a planet of it's a system of 7 planets or so. So this we also found some interesting cases, like we just discussed. There is lesser chances of giant planets found around M-DOS. We only had very few detections made. We could find a very giant exoplanet, which was orbiting a very low mass star, and this has a very larger period of 204. If you happen to look at the residuals, now why I have chosen to show the system. So if you just plot the planet, you are okay, this is a confirmed discovery, we publish it. But if you happen to look at the residuals, you see that there is a trend which is going on. Now, when we followed this trend, so we did not stop observing this target after publishing it, we kept on observing it. Later on, we have now submitted the new paper. It has an additional planet in the system. So this has 2 giant planets in the system. So that is the patience is what is the key. If you keep observing these targets for a very long time, then you end up discovering sometimes more systems here. So this is also a very relatively faint M-type star, and it's very interesting because these are not very common systems that are discovered. Now, another additional aspect of looking at small planets is that M-DOS, as we mentioned, that they have more smaller planets that been detected. Now, what was earlier found out by when people were looking traditionally with planets around solar type stars, and with the additional information that came through M-DOS, people found out that planet population has a distinct bimodal distribution if you happen to look at the size of the planets. So there are planets which are concentrated with a radius of 1.2 our Earth, and then there are several planets which are having a radius of somewhere around 2.2 Earth radius. But there is a lack of planets somewhere between 1.5 to 1.8 Earth radius. And this gap is called as the radius valley, because if you plot the planets as a function of radius, you seem to observe this valley. So this was first of all pointed out by B.J. Fulton in 2017 based on the solar type sample. So planets around solar type stars, there was a large survey which was conducted, and they discovered such things existed. With the recent advent of more and more planets discovered around M-dwarfs, we started to see that this gap also exists for M-dwarf planets. And this is something which CARMENES and many other fellow astronomers are now trying to focus on, and this also happens to be one of the areas that I am interested in. So we tried to look at certain systems where there will be more than one planet in a system, which means that these are multiple transiting planets. And why such a distribution should exist? So there are several theories which try to explain this. One reason could be that maybe that the planets which are situated closer to their host star, since the star is very hot, and in the initial formation years, maybe it emits lot of X-ray radiation, the atmosphere of these inner planets would be stripped of its atmosphere, and what remains is just the core of the planet. That's why the radius of these planets is relatively smaller. And then there are other kinds of planets which can retain their hydrogen and helium atmospheres because they are slightly outwards of the system, and that's why you see some of the planets having a higher radius. This can only be solved if you have systems where you have more than one planet detected, and then you systematically try to understand if really the inner planets have such a distribution compared to the outer planets in the same system. So we did this for one of our papers where we tried to look at similar planets which were planets which were observed around the same host star, and we tried to mark them with the same index. So all the squares that you see here belong to the planets detected around the same star. The stars correspond to, again, planets detected around another star, but the host star remains to be same similarly. So there were 3-4 such systems which are plotted here, and in almost all cases what we found that the inner planet which is there, it has a radius which is consistent with the Earth-like core, which is heavy based on the density, and the planet which is orbiting outwards or further away from the host star, it has a density which is consistent with hydrogen and helium. And how are we talking about the density? We are making indirect measurements because we know the mass by radial velocity measurements. We are taking the radius by the transit, which is TESS here, and that's why we can make a comment on the density of this planet. So this is one forefront research area. This is going on, and then there were several other things. So this is one of the habitable zone M-dwarf that we could publish. So there were 2 planets in the system. This one, the inner one, happens to sit in the habitable zone, which means it has the right temperature to if there is any possibility of supporting life. But there is no evidence of life because that's no any such measurements that we did make. But these will be excellent candidates. Again, as I mentioned, that you should look for biosignatures through atmospheres, transmission spectroscopy. So they are very interesting candidates which can be looked out further. So this was just one candidate that we published which had such signatures. Then there are some interesting things of ultra short orbital periods, which means there is a planet which is orbiting at 7.7 hours. Now, this is very interesting. You have a planet which is orbiting so close to its host star, and the planet mass is less than that of Earth mass. So this almost has a density as that of Mercury, and it's very high. And the planet, if you just make its comparison about how would you explain the density? It can be explained only when you assume that the whole density of the planet is consistent of just iron. So if the planet is completely made up of iron, this doesn't mean that we have found iron there. It just means that the density is consistent with that of iron. And that dense planet is this that we found out through one of our, this is around a G-type star. And this was something very interesting at a very short orbital period. So such period planets are known as USP or ultra short orbital periods. There are several such systems which are present there, but they can also be very interesting to understand what kind of planets can be present. So from ultra short orbital period planets to hot Jupiters to warm Jupiters to Neptune-like planets, there is a whole zoo of exoplanets which is present. So unless we know all of these planets in all different kinds of environment, we cannot make any comment on planets around different kinds of host stars. So it will be interesting to not only look at sun-like stars or massive stars, but also to look at stars which have a lesser temperature. So this will be very effective. Now, I think in the last 10 minutes, I would just like to point out some nuisances or difficulties that we have in planet detections. Now, I mentioned in the initial part of my talk that detecting planets, the smallest of exoplanets, is sometimes very tricky because the stars also has some signatures which affect us. Suppose if we are able to look at this, let's look at this graph. This is the radial velocity contribution of different kinds of effects that are happening only on the star. So star can have granulation. Granulation, I don't know if you are aware a little bit, but it's just like a boiling of tea, how it happens on the convection things which are happening. Every star is made up of plasma and it has this granulation pattern which happens. Then there can be modes on the disk of the star, then there can be spots, and all of these magnetic field spots or these flares, they can lead to variations or cause sometimes spots, or they can call some extra magnetic radial velocity variation. This can be misinterpreted as actual variation from the planet, but in reality, this is not a planet, but it's something else. So what do we try to do? We do systematically look at some lines which are sensitive to magnetic field measurements. For example, we look at H-alpha line, which is a very good proxy for stellar activity. We also concentrate at calcium infrared triplet, or we look at certain other activity indicators. Maybe they might be a bit complex, so let's not talk about it, but just we concentrate on some of the activity sensitive lines, try to see how the width of these lines change. And when we know this, we also try to look at what particular frequency the period peaks. So if you have seen such a signal, so this is nothing but a periodogram. These are 2 interesting signals that you see in the data. So one would conclude that there could be 2 planets because this is a radial velocity periodogram. Then you start to look at other indexes, which is the H-alpha, how the variation is happening in the full width half maximum of H-alpha line, or how is it varying in the calcium infrared line, or there are other indicators. If the period of the radial velocity matches with any of these activity indicator, then this is a red flag, which means it could not be really present because of a planetary signature, but there could be something else which the star is doing, and it's not really a planet. So this is a red flag for us, and definitely you need to do further analysis before you claim a planet at the same period that you see in other activity indices. So there are several diagnostic tools that people take. One of them is the stacked Bayesian periodogram. Simplistically, what you see is you just stack up all your observations and see if the power in the periodogram grows. So if the planet period is, if the period that you see is planetary in nature, like in these first 2 plots, you see that the power in the periodogram builds up. This is just observation stacked with period. This is the power of the periodogram. You see this curve getting pink in color, which means the power is just growing up. And in this rightmost plot that you see, the power was initially low, then high, again it went low and high. So it is not really increasing. The reason is that the stellar activity is never constant. It changes because there are many phenomena that is happening on the disk of the star. So even if you see something at a period of, example, 40 days or 30 days, but if the power is not stable, this gives us a flag that this might not be planetary in nature, but this is only because of something intrinsically that the star is doing. But if you want to detect very large planets, for example, which have variations of 100 meters of second, and there is nothing which affects at 100 meters of per second, this is not a problem for you. But detecting smaller planets, where even the variations are of the order of 2 to 3 meters per second, the planet amplitudes are also of that level, this is a problem. And then we have to really worry and do several such diagnostic tools to confirm whether at that particular period you have a planet or not. So this is another indicator that we use in CARMENES. Because of the broad wavelength coverage, we try to see how your radial velocity amplitude is changing over the wavelength. So normally, if there is a planet which is present, if you make radial velocity measurements in the visible or in the near infrared, the amplitude should remain the same. But if there is a stellar activity signal, the amplitude will depend upon which wavelength region you are looking at, because this is a phenomena which is coming from the variations of the magnetic field. And that's why this is also another powerful tool to understand if the nature of variation is planetary or non-planetary. So we do take care of some of these things, and then we try to model the signatures in together. So this is a confirmed radial velocity curve of two confirmed planets, and this also has a rotational signal imprinted on this. So we have several such modeling techniques that we follow in order to confirm a planet. So in summary, I think conducting long-time baseline surveys to understand planetary architecture is the need of the time. So you confirm a short orbital period 2-day planet, which can be easily confirmed in 6 days. But publishing them and ending this is not the story. Observing stars for a very long time, if you have the time and money, then one should do it. And also, in order to understand planet formation, it's not just one kind of planets that one wants to look at. It is larger planets versus smaller planets. So one would say that, oh, it's so important to only look for planets with instruments like CARMENES or HABs because they are looking for the smallest planets. What is the Indian telescope going to do? We are in Aries also planning to have a high resolution spectrograph, or in India at Mount Abu, there is already Paris, but it cannot detect Earth-like planets. So is it worthless? It's not worthless, because it will also contribute to larger planets, which these extremely precision radial velocity spectrographs will not be interested, because they can invest more time in detecting the smallest of planets, where the moderate sized telescopes can contribute in detection of larger planets. And a consolidated study is very, very important in order to understand complete planet architecture around various stellar types. So understanding not only solar type stars, but also looking at evolved stars, the time. So this is something where everybody of us can contribute if we have the time to do radial velocities, or at least there's a lot of information available on TESS and space-based missions where we all can contribute. So, and the last bit that we spoke of, that stellar activity is a big hindrance to detect the smallest of exoplanets, and a lot of research is going on to remove these signals and to model them accurately. So I think with this, I would like to end my talk, and whatever results that I showed was a contribution from several of the astronomers across the globe in India and abroad. And I would like to thank all of the funding agencies and the institutes. Thank you very much.
Okay, so questions? Yeah.
You mentioned that this is the deduction limit for the planet around the massive star, as well as finding the planet around the massive star is also very typical. This is very rare actually,
It's
because
very
of the high radiation pressure.
Yes, yes.
So how do you say this is there any chance for getting the planet around the massive star?
Yeah, that's actually a very good question. I did not put it in my slides, but this is something recently which I'm interested in. So most of these massive stars, at the consequence of stellar evolution, they will turn into subgiants and giants.
Right.
So when they do this, so suppose a typical A-type star, which will have a very high rotational velocity of 100 kilometers of second, it is not a good candidate to be observed with the radial velocity because of so broadened lines. But if you happen to observe them at a later stage of evolution, then maybe you can impose some limits by saying that these could be the stars which are later evolutionary stages of massive stars. This could be one way of looking at planets at later evolution. But as you said, there haven't been many detections only because of many nuisances. And these stars which are in the AGB stage or subgiant or giant stage, they're also known to oscillate a lot. So any planet where you detect, you need to be careful before you make a claim.
Only this. Now, is there any chance to detect the planet around any giant star and all, like the giant stars which are becoming giant from the solar type star and onwards.
I did not get the question.
Planets around a giant star.
Yeah, so there have been studies even with radial velocity,
Yeah.
but there are also other detection methods which can be used. Now, direct detection techniques like imaging or so, they work well with such stars. Even with Gaia, you would be able to detect. But then there is a limit. You cannot target the space which is very close to its host star. So if you want to image a planet, which we did not talk about in this talk, but these will be separated at a huge distance. With Gaia also, it works well that way. If they are separated at a huge distance, then you can do really the astrometry well, and one can find out how much the separation or some such things will be there. With radial velocity, the detection have been limited. They haven't been higher because of the consequence of how the lines are there.
Second thing that you talk about the stellar activity, because the stellar activity, for example, mostly the problem with the spots and faculae and all, but these are the rotating with the fixed rotation amount, and they are, as you mentioned, that they are changing with the time actually.
Yeah.
That can be done with the simple light curve as well. Not going to, even if you through the light we have a time series data like a test and all.
Yeah.
You can detect them whether it's due to the.
Yes, that is right. So what we really do is the photometry, we can detect them, but this information has to be also put into the radial velocity, because that effect is getting
Exactly.
imposed on the radial velocity. So if that
See,
was
that's what I'm saying to you, that if you have a prior information that you can
Definitely.
supply to the RV.
Definitely we do that. We do that. So that is also there. In some cases where we do not have photometry data, we try to have this long period photometry observations taken and try to have this rotational period measurements. But definitely we do with photometry. Yeah. Yeah.
Has there been a study carried out where we can say that we have discovered all the planets of a particular star?
We cannot make such a statement because
Or we have tried to.
well, we try to do that, but you cannot be anytime sure. You never know. There might be a very distant planet which is
Right.
still waiting to be discovered. So 100% confirmation of all planets in a system is something which you cannot. I mean, even in our solar system, people are trying to detect the ninth one. That extrasolar planets is very difficult to make a sure shot claim that you have detected all. You can always say to this detection efficiency, to this distance, to this period, your survey can be complete. But everything comes with that limit. Anything, if your spectrograph goes better than that, then you start to see that there were additional planets claimed in an already single planet system which was detected 10 years ago. Now we have started to see additional planets.
But they are,
Some planets were killed, which means they are not really there, but some people spuriously identified them.
surveys are there to.
Yeah, they do that. If they have time and agenda in their thing,
It's
some
time
people just
taking.
want to detect new planets and want to look at new stars. But some people are also looking at interesting things which have one planet but want to continue to see more planets later on. Yeah.
So, what is the youngest star in which the planet has been discovered?
I think I am VASP something. I'm forgetting the name, but the age is 27 mega years or so.
27. So all this disk and other things they destroy in 10 million
10
years. So
million
is it possible to detect them in
Yeah, this will be a very, ideally one should be able to look at stars which have lifetimes of around that.
Yeah.
But these stars are also known to be very, very active, and they might be embedded by the disk. So it's hard to do radial velocity measurements, but the ideal would be to look the age of somewhere around 20 million years or lesser than that to constrain where really they would
Is
have.
there any relation between age of the star and the mass of the planet or period of the planet?
Age of the star and mass of the planet. As far as I know, I don't have information. It could be, but I am probably not aware of if there is any such relation. Usually the detection of such planets have been made around like giga-year-old stars. So to really look into this, I must look. I have no idea how they are related.
Yeah, very simple and trivial question. I saw that one information in this, where half of the Jupiter radius, you
Yeah.
find the more number of the planets.
Yes.
So what is the reason for that?
Yeah, reason I don't know. Actually, it's not a simple question. It's a question which many people are trying to answer. This is a very important research aspect. More smaller number of planets are formed compared to larger planets. So we are not observationally
Also,
biased.
the difference is very huge.
Difference is very huge, and this has also escalated after the launch of these many transiting satellites, which has contributed to the detection of many small planets. And there have been also spectrographs which are trying to detect more such small planets have found around M dwarfs. So this is something also in the last 10 years. So for around M dwarfs, there are many planets. This is one thing compared to solar-like stars. More small planets also. This is the second thing. And there are more M dwarfs in our galactic neighborhood. This is the third thing. This could be the consequence, but
And
yeah.
when we are talking on detection, so what is the number? Like how many planets you talking like in overall total?
So this is, I mean, till date, nearly close to 6,000 exoplanets have been discovered. So 5,800. So many of these are small planets.
So
Actually.
this 6,000 number is also true for that one another plot you are telling about the belly structure for the Earth. So
Yes.
they are also almost 6,000.
Yes, only for the ones which we have radius
Yes.
measurements. So not all would have radius measurements. So
Less than
only
6,000.
less than 6,000 planets, but most of them seem to have this valley. And interestingly, since you asked, this valley is not fixed for the type of star. It also changes. So this valley shifts a little bit depending upon the host star. So that's another thing. It also depends on the host star temperature, the value. Yeah.
Very nice talk. So in the radial velocity detection method for the M dwarfs, how crucial is the stellar parameters? Is it crucial at all, or do you use the stellar parameters of the M dwarfs in any of the situations?
Yes, it's very crucial. Actually, if in any detection method, whenever you're trying to make a claim on the mass and the radius of the planet, everything is dependent on it's a ratio. So in the ratio, always in the denominator, you would have the ratio, the radius of the host star and the mass of the host star in the radial velocity and transit method. So if you have no good information on this, your numbers that you claim for the mass and the radius of the planet will be also affected by that.
So how do you get that?
Yes.
Is it using spectroscopic method, or is it?
Yes. So when you do high resolution spectroscopy, you generally have, while you're doing radial velocity, you are taking high resolution spectroscopy measurements. You can use that as well to make a constraint on the mass and radius of the planet. So you can measure the temperature, the metallicity and surface gravity through some sensitive lines, temperature sensitive, surface gravity sensitive lines. And through that, as a consequence, you have an empirical relations to find out the mass of the star and the radius of the star. Or through photometry also one can do that.
So as far as I understand, in the case of M dwarfs, the stellar parameter determination is not very well developed yet.
That's true.
So how do you, in CARMENES, how do you do that? Do you have any idea about that?
Yeah. So we do, again, it's all dependent on the spectroscopy that we do. And ultimately, we try to make these comparisons with some models. So there are these BT settle models or so that we try to make comparison. But as you pointed out, it's a very tricky field where whatever the numbers that you're getting, it's all dependent on the models ultimately. So good improvement in the models will be definitely helpful. We have it more in the solar type stars, but still not very accurately done because of these molecular bands that are present in M dwarf spectra, which is not there in the
solar type stars. Okay, thanks.
So Priyanka, so which gases you think the most crucial ones to find the planet signature, I mean, life signature? Is it the sulfur-based gases? Or?
So methane is one thing that we know. Those information is all based on what we understand from Earth. So methane is there, oxygen, water molecules, and there might be other signatures too. But these are some of the easy things that people are trying to look for. If we want to claim about.
Previously also DMS is found earlier also, or is it recently JWST?
Yeah, JWST is the only one which is trying to, it's able to have these detections. But again, I mean, it's also a very sensitive area to comment on. I mean, these detections, whether they directly relate to life or not, people have very different opinions. Now, those who are very much expert in this field, they've also, the recent thing that was put out in the news, it's also, I mean, we are on YouTube, so okay, fine. Yeah. It's always you can contest the results, but it's a good discovery. But you would ultimately you would need more data to make such confirmations.
The first one found the sulfur-based gas element.
I should
or before also there was.
I am not really sure to make an answer to it, but I think it's one or two. There haven't been many detections to that confidence level. Actually, also matters at what confidence level you are making these claims. Yeah.
Maybe you also address this question because it's kind of associated with what Govind asked. And when you have this, stellar profile and you're trying to use the radial velocity curve to get the planet. Now, if you have multiple planets very close to each other, like for example, when you showed that, okay, with 1:2 ratio, you could say that there were two planets all. So how complicated would the curve get, and how would you, distinguish the different noise that are because of the star
Yeah.
and because of the presence of these two,
Yeah.
closely,
Yeah.
moving planets around?
Yeah, that's a good question. So what really happens is ultimately it all boils down to Kepler's law. So what we in this detection methods, the easiest detected planet is usually fitted and taken out of the system. You look at the residuals each time after the observed minus model fit. If the residuals also show a behavior which could be sinusoidal, you try to fit this until you reach the noise level. That is how the things are done, and you might even fit spurious planets, which are not really planets, but then ultimately you need to see if this detection can be claimed as a planet or not by doing other tests. But the way of fitting planets is this. The easiest one is first fit and then subtracted out from the model, and then you look at the residuals, keep looking at the residuals till you reach the noise level. Minimum threshold is dictated by your RMS of the data. You cannot never go beyond that. I mean, there are cases where people are publishing 2 sigma detections, which means only 2 times the RMS. It depends on, if there is really difficult to make claims and you want to you want to put out a smallest detected planet and make a discovery, then people are doing it. But the general rule is 3 sigma.
Yeah, so Priyanka, you were telling that you will also study the for the massive stars, how planets are, like what is the frequency of the planets and how they are evolving.
Yeah.
So like what kind of study you would like to do, like whether they're massive, like whether these gets massive when they evolve, or like
that's a very interesting thing. I was thinking of looking at giant stars, but then giant stars have their own problems because they can have a lot of oscillations. So at the moment, what I've started with is to look at some subgiant stars. I did not cover anything out of that that we have started from the last 1 year. So we are curating a sample of some subgiant stars which have crossed the main sequence based on their evolutionary age, the log G value, and whatever implication. They could be main sequence stars, but they are definitely beyond their usual main sequence times. And then we will try to conduct a survey with some of these spectrographs that we are trying to get time on. And we will be doing a similar survey, like it might not be a lot of stars, but we'll try to see. So we have some initial results from test data where we only looked at photometry samples. And there we see that there are planets in the subgiant sample, but the interesting bit is that they are not orbiting at a very close distance. Unlike the M dwarfs, wherein you find planets which are very close to their host stars, usually in the subgiant stars, maybe because they have some sort of a co-rotation radius where the planets might just be eaten up by the host star. So they are just not existing there. So this is something which we are early on seeing, just concentrating on photometry data. And with these results, we will be proposing some spectroscopy study on subgiant stars. Yeah.
Ma'am, my question is, we have larger radius planets in the close orbit. We have larger radius planet in close orbit you said due to radiation, and they bloat up. Is it the thermal aspect of the radiation which is bloating it up? They
That is
heat
one
and bloat?
aspect. That is one aspect. In some cases, it also could be that the stars are very active and they would have these the EUV radiation, which is making them bloat up. But usually it is the thermal radiation that bloats up the stars in these hot Jupiters that you see the radius getting bloated up. Yes.
Okay, ma'am. My second question is, we have younger planets and they do have higher eccentricity as they.
It's not necessary, could be, but it's not very necessary that younger planets have higher eccentricity.
Okay, then we can discuss it later.
Okay. Okay.
Any more question here? So, if not, let us thank the speaker for nice and interesting. Yeah, we close now.